In this lecture, we will discuss equivalence between finite state automata and type 3 grammar or regular grammar. Now, what is regular grammar? A regular grammar has the rules of the form A tends to AB or A tends to A, where A and B are non-terminals and single A, this is the terminal string. Means we have on the left hand side we have single non-terminal, and on the right hand side we have a terminal followed by a non-terminal, or we can have on the left hand side a non-terminal and on the right hand side a terminal symbol. Now let's take an example. In this example, what we are doing is that a regular grammar is given. Grammar is NTPS, this is given, and we want to construct the corresponding finite state automata. Fine. Here we will construct non-deterministic finite state automata, because whatever the grammar will be given, that will create non-deterministic finite state automata. Fine. Now, so grammar is given and we want to construct this automata. See, for grammar, G is equal to NTPS. For making this machine or this automata, we need K, sigma, delta, Q naught and F. K will be the non-terminal symbols. The K will be having, the set of states will be having all the non-terminal symbols and a final state. So, this will be the total number of state of the automata, right? The sigma will be the terminal symbols. Okay, so sigma will be taken as terminal symbols present in the grammar. Q naught will be equal to the starting symbol of the grammar. Here grammar has starting symbol is S, and in automata Q naught will be the initial state, right? Final state will be QF. We have considered it that QF is the final state. Now we need some rules to construct the finite state automata. We need this transition function. See, all the symbols are defined here. We have found K, sigma, Q naught and F. Now we need to find this transition function. Now, if we are given a rule A tends to A, then we will be having a transition, this delta. We are at some state, we read some symbol and it contains the B. Fine. So, for this type of rule, we will be having this transition. Fine. Means at state A, we read symbol small a and we go to next state B. Fine. Second rule is, if we have a rule of type A tends to A in production rule in the grammar, then the transition will be that at state A, on reading small a symbol, then we will move to the final state, right? For this production, A tends to A, this is the terminal symbol, then we will be having the transition that at state A, we read this symbol and move to final state. So consider an example. This grammar is given to us. S tends to AS, S tends to AA, A tends to BA and A tends to B. Now the language generated is A to power N and B to power M, where N and M are greater than or equal to 1. Now we need to construct the corresponding finite state automata, right? So the total number of states will be the number of non-terminals union a final state. Here the number of non-terminals are S and A, right? And including one final state, then we will be having 3 states, S, A and this QF, right? S is the starting state. So this will be the initial state in the automata. Now, for A tends to AB, we have a transition at state A. We read symbol A and we move to this B state. So following these rules, we have this first rule, S tends to AS. Then S tends to AS means S, at state S we read symbol A and we remain in the same state. See, the transition is S tends to AS, means we at state S we read a symbol A and remain on the same state. That's why we have this transition, right? The second rule is S tends to A, capital A, right? So for this we will having a transition S tends to A. So this is the transition. This is for S tends to AA. The transition will be S, we read small a and move to the state A. Fine. For the next rule is A tends to BA, means at state A we read symbol B and remain on the same state. So this is the transition, right? For next rule, A tends to B, means we are at state A, we read the symbol B. Now this is the terminal symbol. That means this is acceptable. Means after reading B, we are moving to the final state. That's why we will be having this transition. At state A, we read symbol B and we move to the final state, right? So this is the final automata for the given language. Now, as you can see, this is non-deterministic finite state automata. Cause at state A, we are reading symbol A and we are having 2 transitions. First, we remain on the same state after reading A, or we can move to state A. So this is non-deterministic finite state automata. And this is producing the same language. This is A to power N and B to power M, right? Now let's consider next example. Here the example is this. This is the given language and we want to construct the automata, right? So this is the whole picture. Yes. Now start with, now let's see, total number of states will be 4 cause we have 3 non-terminal symbols. One is S, second one is A and third one is B. So for automata we need one more state which is the final state, right? So the total number of states are 4, S, A, B and the final state, right? Now start with the starting symbol. S will be the Q0, the initial state. Now follow these rules and start constructing the automata. Using this, S tends to AS, means at state A, we read symbol A and go to capital A. We are at state A, we read symbol A and move to state A. Second rule, S, we read B and move to A. On S, we read B and move to A. Third, at A, we read A, then move to B. At A, we read A and move to B. At A, the fourth rule is at A, we read B and go to state B. This is the fourth rule. Transition for fourth rule. Okay? Similarly, 5 and 6. Now, look at 7. Look at rule number 7. B tends to A. Means this is the terminating string. Means at state B, when we read this symbol, we go to final state. So, this is the transition. At state B, we read the symbol A and move to the final state. Right? Similarly, the transition, similarly for rule 8, we have this transition. So, this is the required finite state automata. Right? Now, if we are given a finite automata, then we can construct a grammar, whether it is context-free grammar or regular grammar. The rules will be same only. Now suppose a finite state automata is given to us with number of state, number of symbols, transition function, initial state and the final state. And we need to construct this grammar. Fine. See the correspondence between these two. What is K? K is the set of symbols, set of states. So the K will be this non-terminals. So non-terminals will be nothing but the set of states, right? And these terminal symbols will be the input symbols, right? Means all the input symbols will represent the terminal symbols. Starting state will be the initial state, right? Now everything has been defined. Now we need to define the production rules. Now for production rules, what do we do? For any transition, we are at state Q, we read some symbol A and go to some another state. So for any such transition, we have a rule Q tends to A, P. We are at state Q, we read symbol A and go to state P. So this is the corresponding rule for this transition, right? Now, come to this example. Here, look at this automata. What is the language here? This is A to power n and B to power m, where n and m are greater than or equal to 1. In this case, this is deterministic finite state automata, right? And we need to construct the grammar for this. Now, this is the automata. We need to construct the grammar. So the non-terminals will be the total number of states. Now how many states are there? Q0, Q1, Q2 and D. So all of these states will represent the non-terminals. Input symbols. Input symbols, what are the input symbols here? A and B. So input symbols will become terminals, terminal symbols, T. Now, this is the automata given and this is the grammar generated. Now look at the automata. At Q0, we read a symbol A and go to state Q1. So the corresponding rule is this. Q0 tends to A, Q1. Right? Similarly, Q0 we read symbol B and go to state D. So Q0 tends to B, D. Next is at Q1, we read symbol A and remain at the same state. So the third rule will be Q1 tends to A, Q1. Similarly, Q1, we read symbol B and go to final state Q2. So at Q1 tends to B, Q2. For Q2, we read symbol A and go to D. Right? So this is the rule. Q2, we read symbol A and go to D. At Q2, we read B and remain at the same state. C here. At D, we read A, remain on D, and at D, we read B and remain on D. So these are the rules for this. Now Q1 tends to B, means at Q1, when we read B, we go to the final state. That's why we have written it as this is producing terminal string. For Q1 tends to B and for Q2 tends to B. Cause at Q2, when we read B, we go to the final state. Right? So this is the rule for final state. Right? Now, in this automata, we know that when we reach at this state, then we stuck at this. We cannot go to any other state. So this is called dead state. Right? So that state means we do not want to stuck at this state. Fine. So what do? We remove all the rules which are including this dead state. Fine. Because if we follow these rules which are including that state, then we won't be able to generate any string. Right? So what do? We will eliminate these rules. That's why I have put cross sign here. Right? So after eliminating these rules, the final grammar is this. This is the final grammar. Right? Which will produce the same language a to power n and b to power m, n and m are greater than or equal to 0. Right? Let's consider one more example. Q0, here we are able to read any number of b, then a. This is the final state, and here we can read any number of A's and B's. So what is the language here? See, we can accept single A. We can read any number of B's before A, and after A also we can have any combination of A's and B's. So the language is set of all strings belonging to A and B, where W has at least one A. Okay. So automata is given and we need to find the grammar. Okay. So for this, Q0 tends to B Q0. One rule will be this. So this is the rule. Q0 tends to B Q0. Next is Q0 tends to A Q1. Right? So here it is. Q0 tends to A Q1. At Q1, when we are reading A and B, then we are moving to same state. We are in same state only. So for Q1, we have these rules. Q1 tends to A Q1 and Q1 tends to B Q1. Now look at this diagram. At Q1, when we read A, we are moving to the final state. Right? So what will be the rule? Q0 tends to A. Fine? This is the terminal symbol. And at Q1, when we are reading A, when we are moving to final state, which is the same. And at Q1, when we are reading B, then again I am at the same final state. So the corresponding rules will be for terminal symbols or for final state, we will be having Q0 tends to A, Q1 tends to A and Q1 tends to B. So this is the required grammar for the above automata. Thank you so much.